Lecture 4 Digital Image Processing EC703A Shongita Roy, Assistant Professor, Electronics and Communication Engineering Department, Narula Institute of Technology. Content: Transform of digital images. Importance of digital image transform, Fourier Transform of digital image, Dft. One picture is worth more than 10,000 words. Transform of digital image. Now say xy is a coordinate in a picture or in an image, and the intensity of the pixel is given by f, and at that coordinate is xy. So this pixel is operated by a transformation, that is an operator. That operator is indicated by t. So after operation, the new pixel intensity will be gx, another function. So it is represented by gxy is equal to transform t of fxy. So in an image, it is shown in the figure in a 3x3 neighbor. So whenever we are considering an image pixel, it is surrounded by another pixels, and that pixels have great importance on the pixel we are focusing or we want to transform. So in this example, it is a 3x3 neighbor. It may be 5x5, it may be 7x7, depending on my requirement, and it will be discussed later. Now, image transformation or importance of digital image transformation. So there are a lot of domains where we are working. Now, in general, our universe, around our universe, or in the real world, where we are working, that is the time domain or spatial domain. We are always working on our spatial domain, that is analogous domain, and most of the previous image processings were operated on the spatial domain or on time domain. But there are some few problems associated with this domain. We are unable to separate the frequencies, or we are unable to view how the frequencies are distributed or how the nature of the frequency are in the image. So frequency domain is one of the domain where our main interest is. And as the improvement of digital signals, digital image processing also improved day by day, depending on the VLSI circuit manufacturing or advancement. In the frequency domain, time properties lost. That is also another issue in digital image processing. Now, another domain is there, that is wavelet domain, where we can get frequency property as well as time property. Better to explain that we are operating on both frequency and time domain, and details of the images are not lost, rather than we can find the details locally as well as globally. Now, another importance of working on frequency domain or wavelet domain is, though they are mathematically very complex, but when we are operating in our real life application, the computational complexity is very less, because computational complexity is related to time and space. If we operated in spatial domain, there are a lot of problems we have discussed, as well as time, space is very huge, that is also cumbersome, and associated time is also huge. But when we are operating in the frequency domain or wavelet domain, they are very fast, space is very less. Now, Fourier transform. The Fourier transform is a mathematical formula that relates a signal sampled in time or space to the same signal sampled in frequency. In signal processing, the Fourier transform can reveal important characteristics of a signal, namely its frequency components. Discrete cosine transform. Discrete cosine transform, DCT, is a technique for converting a signal into elementary frequency components. It is widely used in image compression. Discrete cosine transform DCT is an important technique or method to convert a signal into elementary frequency component. It is widely used in digital compression technique like JPG compression. It converts each pixel value of an image into its corresponding frequency value. Wavelet transform. A wavelet is a mathematical function used to divide a frequency given or a continuous time signal into a different scale components. Usually one can assign a frequency range to each scale component. Each scale component can then be studied with a high resolution that matches its scale. Wavelets are mathematical functions that cut up data into different frequency components and then study each component with a resolution matched to its scale. They have advantages over traditional Fourier methods in analyzing physical situations where the signal contains discontinuities and sharp spikes. Wavelets were developed independently in the field of mathematics, quantum physics, electrical engineering, and seismic geology. Interchanges between these fields during the last 10 years have led to many new wavelet applications such as image compression, turbulence, human vision, radar, and earthquake prediction. Wavelet and Fourier transform are the common method used in signal and image compression. Wavelet transform are very powerful compared to Fourier transform because its ability to describe any type of signals both in time and frequency domain simultaneously, while for FT it describes a signal from time domain to frequency domain. Because of that, the performance of FT is outperformed by the impressive ability of wavelet transform for most type of signals, stationary or non-stationary. Fourier Transform of Digital Images, DFT. Brief History. The French mathematician Jean-Baptiste Joseph Fourier was born in 1768 in the town of Auxerre, about midway between Paris and Dijon. The contribution for which he is most remembered was outlined in a memoir in 1807 and published in 1822 in his book The Analytic Theory of Heat. This book was translated into English 55 years later by Freeman. Now, in this picture, there are 4 different sinusoids are there of different frequency, different amplitude, and they are summed, and it is given, the result is given in the 5th wave, and it is the summation of above 4 sinusoids. This is the main concept behind Fourier transform or Fourier series. Preliminary concept. Let a complex number C is equal to R plus Ji. J is an imaginary quantity. The conjugate of C is known as R minus Ji, and polar coordinate representation of C is equal to C modulus of C cos u plus J sin u. Fourier series. A function ft of a continuous variable t that is periodic with nature with period t can be expressed as the sum of sine and cosine multiplied by appropriate coefficient, and this is known as Fourier series, and it is given by this function. Cn are the coefficients, and the expression ft is an expansion of sines and cosine following from Euler formula. Impulses and their shifting property. Central to the study of the linear systems and the Fourier transform is the concept of an impulse and its shifting property. A unit impulse of a continuous variable t located at t is equal to 0, denoted by dt, is defined as del t is equal to, for t is equal to 0 it is infinity, and t not equal to 0 it is 0. And it is constrained also to satisfy the identity integration minus infinity to t infinity del t dt equal to 1. A more general statement of the shifting property involves an impulse located at an arbitrary point t0 denoted by dt minus t0. In this case, the shifting property becomes integral of minus infinity to infinity ft del t minus t0 dt, that is indicated by f with t0. Unit discrete impulse. Let x represent a discrete variable. The unit discrete impulse dx serves the same purpose in the context of discrete systems as the impulse dt does when working with continuous variables. It is defined as integration of minus infinity to infinity ft del t minus t0 dt is equal to ft0. Clearly, this definition also satisfies the discrete equivalent summation of x equal to minus infinity to infinity del x equal to 1. The shifting property for the discrete variable has in the form of summation of minus infinity to infinity fx del x is equal to f0, or more generally using a discrete impulse located as x is equal to x0, that is equal to summation of minus infinity to infinity fx del x minus x0 is equal to fx0, and it is shown by this figure right hand side. An impulse train S del t defined as the sum of infinitely many periodic impulses of del t units apart, and it is given by S del t is equal to summation of minus infinity to infinity del t minus n del t, and it is given by the right hand side below figure. Now the Fourier transform of function of one continuous variable, and this function is given by minus infinity to infinity of ft e to the power minus j twice omega t dt, when mu is also a continuous variable because t is integrated out. Therefore, Fourier transform of ft is a continuous only of mu. We denote this fact explicitly by writing the Fourier transform as Fourier transform of ft is equal to f of mu. This is the Fourier transform of ft can be written as below. Conversely, this can also be reversed back, and that is inverse Fourier transform. So ft will be inverse Fourier transform of f of mu, written as ft is equal to integration minus infinity to infinity f mu e to the power minus e to the power j twice mu t d mu. Now Fourier transform of rectangular pulse with mathematical expression is given above. It is a rectangular pulse, and the below picture is showing first one is a sample function and its Fourier transform, then its spectrum. All function extend to infinity in both the direction. These are the references. Thank you.